Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the content of the universe, how the universe evolves, how things interact. A lot of cool stuff happening, especially in the very early universe. I love being a scientist. I love chatting about science. And yeah, I love coming here and chatting to everybody about all of the cool things I get to work on and about what it's like being a scientist and, about cool stuff in general. For anyone who's new here who doesn't know how this works, this is an interactive stream. This means that you can all ask me any questions you want, and I will do my best to answer, which means the direction of the conversation is entirely up to you. I do not have a topic prepared today, so this discussion, this conversation will go basically wherever you all want to take it. Hello to all of the regulars joining. I see we have Scott, we have Prath, we have two of the Davids in here today. Great to see you all. I know by now there's like 4 Davids who tune in regularly. So great to see all of you here as always. Great to see Ange as well. Great to see everybody always coming in. I'm still so surprised that you all come in week after week. It's been 9 years now and you're still all, or 8.5 years, and you're all still here every week. And I very much appreciate those of you who come back every week. And for any first-time viewers, welcome. It's great to have you here. If you haven't done so yet, please do subscribe, leave a comment, like the video, do all of the usual YouTube things. It really does help boost engagement, and then I get to reach a broader audience and then talk to more people about how amazing studying cosmology is. So please do all of the usual YouTube stuff to boost engagement. If you're watching over on Twitch, hello to the Twitch viewers as well. You can also join in the conversation. I will see comments from Twitch, I will see comments from YouTube, whichever platform you're watching me on. Feel free to jump in and join the conversation as well. I know there's not many of you watching on Twitch yet because I haven't built up an audience on Twitch, but those of you watching on YouTube, great to have you here as well. You don't want to comment from Scott here about blue dwarfs. We did cover blue dwarfs at some point. I'm sure we've covered it. That's a done topic. Never need to revisit that topic again. Comment from David Howden. Don't want to miss the week when you reveal where you have been hiding the dark matter. It would be really fun, right? If I start the stream like, so big announcement, here's dark matter. Here's one I made earlier. Unlikely to be anytime soon because, dark matter is extremely difficult to find. So for anyone who doesn't know, the universe has 3 main components. Hey, David Dunn, thanks for testing the Twitch stream. I saw you comment on YouTube and now on Twitch. Thank you for testing that as well. Always nice to know that Twitch is up and running as well. So the universe has 3 main components: everything we see, everything we're accustomed to, everything from me to my coffee mug to the stars you see at the night sky. All of this is normal matter. Normal matter only accounts for 5% or 4.9% of the energy budget of the observable universe. Then there's another 26.2% in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally, but doesn't interact electromagnetically. This means that dark matter is essentially invisible. Makes it very, very hard to study something that is completely invisible. And then the remaining 68.9% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that's pretty much everything we know about dark energy. How do we know these things? We know these things thanks to, I went the wrong way. We know these things thanks to the cosmic microwave background radiation, this thing here. This is an image of what the universe looked like 380,000 years after the end of inflation. The different colors show you regions that are slightly hotter and slightly colder, but we're talking about a tiny, tiny, tiny difference, like 1 part in 10,000, 1 part in 100,000 difference in the temperature here. And thanks to these hot spots and cold spots of this light produced in the very, very early universe, we know these numbers of how much is in the universe. And indeed, for anybody keeping track, it took me less than 5 minutes to get the CMB up on screen today. It's always a race to see how long it takes me, and it is never long. So less than 5 minutes today. Okay, so this was just a quick info dump there of dark matter, dark energy, just to give you an idea of the type of things you can ask me about. So there was a comment here about where have I been hiding dark matter, and this is because I do indeed work on dark matter. So as I said, dark matter is this weird type of thing that we can't actually see. But what I have been trying to do throughout my career, throughout the God knows how many years I've been in academia by now, it's hard to keep track, and it has definitely been a few. I asked the question of what if dark matter isn't as invisible as we think? What if dark matter maybe bumps into things in the early universe? What if dark matter maybe bumps into things today, just a lot less than we thought? Or less, just a really, really small amount? And how would this affect things like the cosmic microwave background radiation or how galaxies look in the night sky? So a lot of what I've been working on in the past is asking the question of how can we use the universe around us to understand the properties of dark matter, like what can dark matter do. So imagine you're in a forest at night and you hear some animal walking by, right? You can't see it. So then you try to figure out clues about what this animal is based on what you can figure out. So then you're like, okay, maybe if I hear a twig break, then it's not a bird flying past because it's probably walking, so it's probably not a bird. Maybe if I hear it make a noise, I can figure out what type of animal it isn't or what type of animal it is. So you try to listen to all of these clues to figure out what this animal is, even if you can't see it. So that is kind of like what it's like trying to find dark matter. We can't see dark matter, but we can try to infer what it is from its other behavior. You know, based on how galaxies look, you can guess if dark matter did one thing or did another. Based on the amount of light you receive in the night sky, you can kind of guess, like, okay, dark matter must have done this, can't have done that. Looking at how light bends in galaxies, you can say, okay, there must be something there that behaves a bit like dark matter. And that's what I work on, trying to ask or that's what I have worked on mostly in the past, is trying to ask the universe, what can you tell me about dark matter? So that is a very cool thing. You're often in a forest at night trying to work out what's there. Yeah, I guess as an entomologist or working with moths and with bugs, that's kind of part of the job. I rarely find myself in a forest at night trying to figure out different animal species, fortunately, unless I go camping. And then I'm kind of worried about what animal species might be out there. But I'm rarely out in the forest at night trying to figure out what different animals are. Okay, so I know I just jumped straight in there to dark matter CMB. As always, the idea here is that you can ask me anything you want about academia, about physics, about dark matter, about CMB, about gravitational waves, about what it's like being a physicist, about what it's like living in Finland, basically anything you want. The idea here is that you really can ask me anything. This has the AMA in the title. This means ask me anything. So any questions you have, you are welcome to ask them. And I will do my best to try to answer your questions. Now, of course, I will not have all the answers. Any scientist who claims to have all of the answers, do not trust them, because we do not have all of the answers. We just have some of them, and those that we don't know, we try to figure out. So never trust a scientist who claims to know everything. And I will always be honest and upfront with you here. If I don't know something, I will tell you. If I don't remember something, I will tell you. And sometimes we try to figure it out together. Sometimes I write down notes and then never look at them again. If like, look at this topic, and then I forget to ever look at that topic again. But in general, the idea here is that you can ask me literally anything you want. There's no question off limits. If you ask me something too personal, I might not answer, but otherwise just go ahead and ask me whatever you want. Let me just make sure that I said hello to everybody who joined in here in the comments. I said hello to it's a bunch of people here. Hello from Twitch, yes. Okay, we have a long question from Scott. Let's go for that one. You get that the proportions of baryonic and dark matter could be calculated, but how exactly did you guys come up with dark energy again and the percentage? I'm so glad you asked that question, and the answer is the same way we come up with other things. So we have this amazing map here, the cosmic microwave background radiation. And this, as I mentioned before, is the earliest light we have in the universe. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. So in the very early universe, you have three main components. You have protons, you have electrons, and you have photons, as photons being particles of light. As the universe gradually cools down, the protons and the electrons can combine together to form the first hydrogen elements, the first hydrogen atoms. Once the protons and the electrons have come together, the photons can travel freely. So the photons, the particles of light, break away and start traveling freely throughout the universe. Now, in the early universe, you also have dark matter. Dark matter at this point is no longer talking to other things, it's just there doing its thing. But there are going to be regions or places in the universe where you have more dark matter and places where you have less. This means that because dark matter is interacting via the gravitational force, dark matter is going to pull the hydrogen towards it. It's going to pull the protons and the electrons towards it. So once the protons and the electrons combine together and the photons can break away, the particles of light can take away, there's going to be more hydrogen in the places where there is more dark matter. So based on this means that then the photon has to escape the gravitational pull of the dark matter before it can travel throughout the universe. So it's going to take a bit longer to do this, so its energy is going to be different. It's going to be slightly colder than the other photons. So this means that basically the spots here that are slightly bluer, the colder regions, mean there was more dark matter in the early universe in that spot and more normal matter. The spots that are slightly redder here, the hotter regions, correspond to places where there was less dark matter in the early universe. So this is how we can use this map to get the idea of dark matter to normal matter. Now, your question was about dark energy. So dark energy gives us the expansion of the universe, which means that since these CMB photons were produced and they've been traveling towards the CMB, cosmic microwave background radiation, since this has been traveling towards us, it gets redshifted. It gets shifted because of the expansion of the universe. If you have, let me get out my trusted slinky, which is close at hand now and just had a stress ball inside it, so I had to change that. Everything has a wavelength in the universe. Any particle also has a wavelength. This wavelength can be stretched. So as a photon, this particle of light is traveling throughout the universe. If it starts like this, it's going to gradually stretch and get redshifted. As the photon moves throughout the universe, it's going to stretch more and more and more. This is the redshift. It's going to move towards the red end of the electromagnetic spectrum. But if this is happening in a universe that is expanding, these photons are traveling, the universe is expanding, then this redshift is going to change. So by the time the CMB photons reach us, they've experienced dark energy. They've experienced the expansion of the universe caused by dark energy. So then when we look at this map, we have several things. We have everything that happened up to the time when dark matter and photons and all of that happened. And then we have everything that's happened since, in the time the photons has traveled towards us. And that gives us a good understanding of dark matter and dark energy as well. But I'm going to be more precise about it. So when we have this map here is 380,000 years after the end of inflation. And while this figure is very, very pretty, this is not really the science behind it. In order to get the science behind that, what we do is we take this map and we take its fingerprint, basically. So we ask, how many blobs are there? How many big blue blobs are there? How many big orange blobs are there? What kind of size are these blobs, these temperature blobs? And then we make this figure here. We make this plot. So this is basically the fingerprint of the CMB, the fingerprint of the power spectrum, of what we saw before. We call this thing the power spectrum. It is the fingerprint of the big, pretty map that you saw before. What you can see here on the vertical axis is the temperature fluctuation. So this is how many blue versus orange spots there are. And what you can see on the horizontal axis is the size. So for an example, the first one is if you cut the sky into 90-degree chunks, how many blue and orange blobs do you see that occupy like 90% of the sky, or a 90-degree angle on the sky? And then you go down to smaller and smaller angles. What you can see here in red is the data we get from the CMB map that I showed you. And what you can see in green is our best prediction. Dark energy plays a role here. If you look at the first three peaks, you have a very, very clear first high peak, and then you have the two second peaks. The first peak gives you the amount of dark matter versus amount of normal matter, and the other peaks do give you the amount of dark energy as well. So if you had a universe that instead of 68.9% dark energy had 5% dark energy, your green curve in this figure would look vastly different. If you have a universe where you put 5% dark matter instead of 5% normal matter, this green curve would look very, very different. So what we do as scientists is we play this game 1 billion times. We run 1 billion different simulations of the universe in our computer. In each one, we change one thing. We change the amount of dark matter, we change the amount of dark energy, we change the age of the universe, we change things. We try 1 billion different combinations. And then we find which one of our simulations fits the data. The data is the red dots here coming from Planck. The green curve is what we found best describes this data. And this green curve is what gives us 68.9% dark energy, 4.9% dark matter, and 4.9% normal matter, and 26.2% dark matter. So the question from Scott was, how do we know the amount of dark energy in the universe? The physics behind it is it's related to how the particles of light then travel towards us in an expanding universe. And specifically, when we pull apart this figure, this is where we get the number from. So hope that answers your question. I love that question, how much dark matter, how much dark energy, and it allows me to show the actual scientific plot behind the very, very pretty plot. I mean, we've all seen this plot hundreds of times. This map is so pretty. But the plot behind it, the thing I just showed you, that green line, that is where the physics is. This is a pretty version, but the other one is where the physics is. So yeah, we know about the amount of dark matter and dark energy because of the cosmic microwave background radiation. Okay, there were a couple of questions here about X-rays that I just glanced at, so let's go and get through those now. Question from Mito here, and of course, as always, feel free to ask follow-up questions. If something I say is not clear, you can ask me. If you haven't understood something, that's on me. for not explaining it properly, please do ask again. I've heard science outreach talks sometimes where people say, like, that was amazing, but I didn't understand anything. Then the person is not doing proper science outreach. If you haven't understood something, I can assure you it's not you. It's because I didn't explain it properly. So please do feel free to ask questions again and again. And if something's not clear, let me know, and I'll try to explain it in a different way. If you have follow-up questions, also feel free to just jump in at any point. This is a conversation. You can join the conversation at any point. The chat is always open. And as you all know, there is one main rule on Cup of Cosmology, which is there are no stupid questions. I have never been asked a stupid question on Cup of Cosmology, so feel free to ask away. Okay, let's go to the X-ray question I just saw here by Mito. Largest ever catalogue of X-ray sources is published. What does it offer for cosmologists? Excellent question. So an X-ray source is something in the universe that emits in the X-ray range. So we have the whole electromagnetic frequency. X-rays are rays that are at a specific band of the electromagnetic frequency. There's a lot of things that produce X-rays. For an example, there are some active galaxies, so the center of galaxies can produce X-rays. There are a lot of stars that can produce X-rays. This is something we know how to measure. We set up a detector, we look for X-rays, we can pinpoint it. This is something that is very, very useful if you're doing astrophysics. So astrophysics is more about the ingredients inside the universe. So what is happening really inside? What is happening to the galaxies? What is happening to the stars inside the universe? Whereas cosmology is kind of how all of this fits together. They are very, very closely related. There is a lot of connection between astrophysics and cosmology. There is a lot of overlap. Now, this catalogue of X-ray sources is especially important for astrophysicists, but for cosmologists, it doesn't really give us much, except it will help us understand things like how galaxies form, how galaxies evolve, maybe. And then it's something that we can use. So having this type of thing is extremely useful. It's not something that, sorry, 1 sec. It is not something that is going to affect my work directly on dark matter, but there are people who are trying to use, for an example, X-rays produced in the center of our galaxy as a detector of dark matter, as a way of testing dark matter. Because you can have some models where dark matter produces X-ray radiation. So if you find too many X-rays, you can try to tie that to dark matter. So having a catalog of X-ray sources is a great resource to have. It's not something that I personally am going to need or going to use because I work on very much cosmological data sets, but having a catalog of X-ray sources is very, very, very cool as well. Yeah, it can help us understand things like galaxies, things like planets. There are people, or sorry, things like stars. There are people trying to use X-rays to study dark matter as well. You will always find uses of these things. And I think it's very cool that a lot of data in science is made public. Now, of course, there's always what usually happens with big collaborations or big experiments is once they get the data, there's a short period of like a year or 6 months where the data itself is kind of embargoed, so that the people who have achieved the data can get the first results, the first publications. And I think this is very, very fair, because if you work on one of these experiments, it's a long time coming, right? There's a lot of years of work that might not have many publications. And unfortunately, academia is very much focused on this publish or perish mentality. So once an experiment has released its data, there's usually a short period of time where the main results are announced, but then the data is embargoed, so that the people who put in all the effort in obtaining this data get the first go at analyzing it. But then usually after about 6 months to a year, depending on the mission, all of the data is made public. And then anyone can play about with it. And that's when you can come up with random new ideas. So the fact that this catalogue of X-ray sources is now public means that if there's anything you want to do with X-ray data in the universe, now it's out there. Now you can use it. And this is always a very, very good thing. So while it might not affect my day-to-day work, I think it's very cool that we now have this big source of X-ray catalog, this big X-ray catalog of this catalog of X-ray sources. It's always very cool when we do that. I've seen a follow-up comment here by Ben. We have seen AI being used today in medical diagnosis, such as analyzing X-ray or MRI images. When do you think it will be useful in the search for dark matter? So I think there are a lot of very, very good use cases for artificial intelligence, or for these large language models, for these algorithms, for these kind of machine learning techniques. Some of these applications are very good, some are less good. I think something that it's very good at is image recognition. As you mentioned here, it's being used in X-rays. These should always be reviewed by a medical professional as well. But it does it does give us another tool or gives doctors another tool to play with or to use in order to get their diagnosis. Now, in terms of science, in terms of physics, there is a lot that can be done with machine learning. I'm very, very reluctant to use the word artificial intelligence because there's nothing intelligent about these things. They are basically numerical processes. We know what's happening. There is no thought involved. Like the machine itself is not in any way being intelligent. It's doing exactly what it was programmed to do, if that makes sense. So these machine learning techniques have a lot of applications, and I think image recognition is something where they really do shine. It's something they really do know how to do. So there are some examples of like classifying galaxies where it could be very useful, especially with experiments like the Dark Energy Survey, where you get thousands of images of galaxies, and based on the shape of the galaxy gives you a lot of information. So that is something where a machine learning technique would be really useful because you can classify these galaxies based on shape very, very, very easily. Then, of course, the Dark Energy Survey, as the name implies, is studying dark energy and also looking at some properties of dark matter based on how much these things are distorted. So for things like that, I think machine learning techniques can be very useful. And using them specifically for image recognition is something that is very, very cool. As for the direct search of dark matter or any type of search for dark matter, it's quite hard to see a valuable use case, for me personally, of machine learning, because a lot of what we do is based on so, okay, I do have an answer to that actually. So, a lot of what we do is kind of running different simulations and modeling what the universe would look like if you have different dark matter models happening. So, there is not so much process these images and tell me which one looks closer. It's more about the underlying data. Now, something where we can use machine learning techniques is, for an example, to speed up these simulations. So, something I've worked on a lot is trying to figure out how we can use data from very small, so in between galaxies, there's a lot of dust, a lot of hydrogen dust. But this dust is following the underlying dark matter, or it's following the dark matter. So understanding this hydrogen dust, or where this hydrogen dust is in the universe, can really help us understand dark matter. However, to use this information from this galaxy dust, we need to run simulations, and these simulations are extremely expensive to run computationally. This means that usually it takes like 3 weeks to get one of them, and you need about 10,000 of them. Of course, this is not feasible. So what I've worked on extensively, or a lot throughout my PhD and postdocs, is building kind of an interpolation scheme. So you run 10 simulations, and then you fill in the gaps. You kind of imagine what you extrapolate. You infer what's going to happen based on these corner plots, these corner points that you have. It's kind of like if you're watching a football game, you might watch the first 5 minutes, then you tune out again, then you look 20 minutes in, then you watch half an hour in, and like every 10 minutes you glance at the football game and then you go back to doing something else. And then someone asks you, can you tell me what happened in the football game? And you try to fill in the gaps based on the information you have. So this is kind of what I do with this information about the dust in between galaxies. Like I take a few simulations and then try to infer what happened in between. And that is something where we can use machine learning techniques. So I'm not currently in my work, but we could, for an example, use machine learning techniques to do this inference, to figure out what is happening in between. In a similar way, if you like learning language models like ChatGPT, personally, I don't. It's a glorified chat predictor, but if you like this and you don't mind the carbon footprint of it, you could ask it like, okay, at time 0 of this football game, this was a score, this is what was happening. At time 5 minutes in, this is the score, this is what was happening. And then at the end, you ask, give me a summary of the football game, and it will give you a pretty detailed summary. So this is using kind of this interpolation technique, inferring the information you don't have. This is something that you can use machine learning techniques for. So while I'm not directly using them, you can use them in this application, for an example. And then you could say, okay, based on how this dust behaves, I'm learning about dark matter. So there are ways where you can use machine learning techniques to speed up some of the processes we do to search for dark matter. But I think this is something that should always be just another tool in our toolbox, right? It's not an answer to all of our problems. It's not going to solve everything. It's not something like, okay, now that we have machine learning, we don't need to do physics, we don't need to do dark matter research. It's a tool. And it's a tool that, if used properly, can be very useful. I feel like there's been a lot of people kind of using machine learning where you don't really need to, just because it's trendy and it's catchy and it's in fashion right now. It's like the cool thing to do. And then it leads to a lot of dilution of places where you can have random stuff on machine learning where you're like, why? This was pointless. There was no need to use machine learning for this. And this is something that makes me personally a bit reluctant to use machine learning techniques, because there's always a question of, is this the right thing to use? Am I using a hammer when I should be using a screwdriver? So I think, okay, this was a very long answer, a very rambly answer, because I'm not a huge fan of machine learning personally, but I think it's an amazing tool that can be used for a lot of things. The fact that it's being used in medical diagnosis is amazing. I think it's something that can help physics in some regards, but I think we should always ask the question of, should we really be using this tool in this circumstance? And is this the right tool for the job? And is there something else I can be doing instead that perhaps is slightly less computationally expensive, less carbon intensive, less water intensive? Because machine learning, like ChatGPT, uses a ridiculous amount of water. Just putting that out there. Okay, so that was a very long answer. People who are regulars here know that I can talk a long time about artificial intelligence, but it's not something that I use myself. And artificial intelligence in quotation marks. Hello from Mexico City on a trip. Great to see you, Paul. Thanks for popping by. Thanks for dropping in. I did not, in fact, talk about blue dwarfs. I made a joke about the fact that I never talk about blue dwarfs, but you did not miss anything about blue dwarfs. Okay, moving on to the next question. I love that we've got a very diverse question so far. We've looked at X-rays. We're now looking at, dark matter, machine learning. We went on the talk at the very beginning about CMB. I love that the questions are very varied and very broad. Okay, hey Ian, great to see Ian here in the chat. Very nice to see Ian here. Ian is actually the reason that I am live streaming, so no scientists in the room. Confess that it's been helpful to me when staring at a blank screen and blinking cursor to get increasingly georetic gears turning. Yeah, so I think ChatGPT or all of these things are in general a tool, and some people find it very helpful. I know some people in my group, in my work, use it to start writing code if you're not sure how to get started. So again, I think there are very good cases where you can use it. I think it is something that we all should question, like, is it the right tool for this? And especially, I would really like to see more talk about the carbon impact of things like ChatGPT, the amount of water, the amount of electricity that were used to generate the training data, and also for the queries. And then it's a question of, is that asking ChatGPT one thing a day is probably okay. Asking ChatGPT 100 things a day might blow up your carbon impact, your carbon footprint. And that's something that I think has not been discussed as openly as I would like it to be. So I'm definitely not complaining about people who use it for very valid reasons. If you have fun with ChatGPT, if it helps you do your job, great. But I think just be aware of, is this a tool you should be using for the job? And I would very much like to see people more honestly discussing the carbon impact of these things before asking it to generate 5,000 random things that are amusing. Because, yeah. But nothing against people who use it, of course. Okay, let's carry on with the questions here. I know there were some very cool questions, and as people always know, machine learning, ChatGPT, that's an easy way to get me to talk for a very, very long time. I have a lot of opinions on that topic. I have a lot of opinions on a lot of topics, actually. Not all of them are great. Okay, question from Prath here. Have we discovered all the standard model particles there are? Is it possible there are quarks that don't last long enough without decay for even the best of our detectors to catch? I love this question. This is a very, very cool question. I would like to bring up my standard model picture to answer that question. Now, the problem is I recently changed the order of all of my slides, because in Restream, I can't actually show individual images. I have a slide deck, I have a PDF, and it currently has 45 images in. And I used to have memorized that the standard model was on image like 32. And then last week, I decided to move all of my images around to a much more logical order. And now apparently it is image 18. Good to know. Standard model of particle physics. Okay, so the standard model of particle physics are the building blocks of all of the normal matter in the universe. So that 5% that we were interested in. In the standard model of particle physics, we have three main known families. Well, first of all, we have two. We have bosons and we have fermions. The bosons are the ones here seen in red and yellow, so the two rightmost columns. And the bosons are the ones that tell everything else how to behave. And the fermions are the 12 that you have on the left, the first 3 columns. And these are the ones that are the building blocks themselves. So the fermions are the ones that give stuff things, and the bosons tell the stuff how it can behave. Inside the fermions, we have 2 groups. We have the quarks and we have the leptons. The quarks cannot be found alone. You will never find one up, one charm, one top. You will always find them grouped together. So there are 6 quarks, up, down, charm, strange, top, bottom. These are in 3 families. The first family is up, down. The second family is charm, strange. The third family is top, bottom. And then you have 6 leptons, 3 electrons and 3 three. So we have electron, muon, and tau, and each one of these has a corresponding neutrino. Standard model of particle physics. It doesn't matter if you don't know all of these building blocks. It doesn't matter if you know what all of these things do. But these are the 17 building blocks of the standard model of particle physics. Everything we know of, like protons, are made up of ups and downs. Neutrons are also made up of ups and downs. If you want to get an atom, you throw in an electron together. So all of these pieces play a role in the universe around us. We have the 12 here that are the main building blocks, and we have the 4 main bosons, and we have the Higgs boson that we kind of don't know how to put together with everything, but it is there. Someday, maybe we will figure out how to put gravity into this picture, but for now we don't. So the question was, is this complete? Could there be other things? Now, behind this nice picture here of these 17 building blocks is an extremely complex mathematical theory. And this mathematical theory is what is called the standard model of particle physics. Now, we don't have any reason to believe that there should be more particles in this part of the standard model. Like mathematically, it seems like the standard model is complete. It has the pieces that we need. It's there. So it doesn't really seem like, where would you put another quark, for an example? Because here we already have these like 3 families. We have an up, down, we have charm, strange, we have top, bottom, we have the right properties. What kind of particle would you try to add here to make it complete? So in general, the standard model is considered to be complete. Let me just go back to the question again. So the standard model is kind of considered to be complete, but that doesn't mean that we've explained everything. For an example, gravity. How does gravity fit into this diagram? We don't know. Is there a particle that could explain gravity? If so, we'd call it a graviton. And then we say, okay, this is also part of the standard model now, I have decided. You know, it's always a thing that we say the standard model is complete until we find something else, and then it's like, okay, the new version. It's like when you're writing a paper and you call it final. Final V2, final V3, final, absolutely final. You know, it's always final until it's not. So right now, the standard model seems to be complete until it's not. So gravity is something that we haven't yet put there. Could there be gravitons? How would that fit in? Where would that go? It would be a boson, but how would it behave? Then you can ask the question of like, okay, what about antiparticles? How do they fit in? Then we say we have this whole like separate thing, which is the antimatter, which you don't need to put as the standard model. It's kind of included. And then you can do fun things like supersymmetry. Now, the idea of supersymmetry, it's a type of string theory model. And the idea of supersymmetry is that every one of these particles here would have a supersymmetrical partner. So for the up, you could have a symmetrical version, which would be the S up. For the top, you could have a symmetrical version called the stop, or S top. Now, these are ones that are hypothetical. We have never found them. And then there's the question of, if we find supersymmetrical particles, are they actually part of the standard model, or are they the supersymmetric version, like the mirror image of the standard model? So we don't have any reason to think there's a missing particle in the standard model, but there are things we don't understand. We don't understand how gravity would fit in here. We don't understand things like why neutrinos have mass, because we expected them not to have mass, and then turned out that they needed mass. So then we were like, okay, now neutrinos have mass. This is part of the standard model now. So then from a mathematical point of view, it seems like it's complete. We're not expecting to find more particles here, but then people are looking at the idea of short-lived particles or long-lived particles that decay either very quickly or in a very long time. How would that fit in? If we find dark matter, is it going to be similar to the standard model? Is it going to be something new entirely? So it's a very nice question here. My short answer is we don't expect to find, like, mathematically, we think the standard model is pretty good. We don't expect to find, we're not looking for any missing pieces. We're not looking for a missing piece of our puzzle. But we might suddenly find a whole new set of puzzle pieces that we need to fit in at some point. If that makes sense. If not, as always, please do let me know. Okay, let me just catch up on the last comments, because now it's a fun thing where some of you are replying to questions I've already answered, and some of you are asking new questions. So then it's going through and making sure I'm replying to the right questions at the right time. So let me just read the comments and get back to you. Let's see, where were we? You've seen enough movies where the robots kill us? Yeah, but usually, yeah, I think we're very far away from killer robots. Like, based on where we are right now with machine learning, I would say a killer robot is way, way, way far off into the future. So I'm not actively worried about robots taking over the world. I am much more worried about other ethical considerations of machine learning, like the fact that the people building these algorithms, these machine learning techniques, have biases and are putting these biases into the computer, and that is a problem. So, that is something that worries me a lot more than artificial intelligence raising up and taking over humanity. That, honestly, I'm not so worried about that. I'm more concerned about the biases we are putting into these machines that we are training. Okay, let me just double check here. In school, they told us that electrons were made of quarks as well. No, electrons are not made of quarks. Electrons are their own particle. I think, yeah, electrons are not made of quarks. If someone told you that, I'm sorry, but they were wrong. Okay, the question here, I've seen there's some other questions, but again, just coming back to these, the ones about the standard model here. There was the question here by Paul of, would the hypothetical inflaton fit into the standard model? Great question. So we think in the early universe, there was a phase where the universe grew exponentially. So it went from being very, very small to being ridiculously big. This is something known as inflation. Now, inflation is hypothetical. We have not yet found any direct proof of inflation. So, inflation, we don't know what caused inflation, how inflation happened, what it looked like. And the biggest reason for that is that inflation kind of deletes the memory of everything that came before it. If we look at this figure here, you can see this is kind of the approximate history of the universe. We have this starting point, and then we have this rapid growth. This would be inflation. So depending on what model of inflation you believe in or which model you like, you can have a particle called the inflaton, and this inflaton particle is what produces inflation. Now, the cool thing is that after inflation, this inflaton, this particle, would then decay into the standard model particles. So then if you consider the inflaton to be part of the standard model, then there's a problem that it's kind of like it's the one that produced the standard model. So where would you put the inflaton in this diagram? You probably wouldn't. So I think in general, when we talk about this inflaton, there's particle that caused inflation, which, again, hypothesis, not yet, this is one of the ideas, one of the models, one of the theories. But where would you put this inflaton? We don't usually put it as part of the standard model, but rather something else entirely. Hope that makes sense. So the inflaton could be connected to the standard model if the inflaton is real, but it probably wouldn't be part of the standard model. Okay, I feel like I'm lagging behind on comments, partly because I just spent like 15 minutes talking about machine learning. Oh, I forgot I have tea here. My tea is going to be cold by now. It's an infusion anyway. It's not real tea, so it doesn't matter if it gets cold. Okay. Then there was a question by Scott. Let me see, about the moon. Let me just read that. Question was about apparent size of the sun and the moon being almost the same, and the feasibility of a celestial body taking up a large portion of the sky. So it's very, very cool that we happen to live on a world where the size of the moon in the sky and the size of the sun in the sky is the same. It's very cool because then you get things like eclipses, and you can get these very nice annular eclipses where you just have like the ring. And this is because the sun looks the same size in the sky as the moon, and there's no scientific, there's no reason this should be the case. You could have a star that looks much bigger. You could have a moon of various sizes. It just so happens that ours are approximately the same size in the night sky, and that is pretty cool. In the day sky as well, in the night sky, in the sky in general. And it's pretty cool that they're approximately the same size, but there's no reason for this. It makes sense. It helps, if the sun were a lot bigger, but then we'd probably be closer, and then it might be too hot. If the sun were a lot smaller, we might be too far away. As for the moon, there's kind of an upper limit. Like if the moon were too big, then it would be fused with the Earth because it would gravitationally attract too much. But, if you were on Jupiter, for an example, you'd see a bunch of moons in the sky of various different sizes. If you were on a planet that has another planet close by, you might see a very big planet in the night sky. or in the daytime sky. So there is really no limit other than really if two objects are too big or too similar in size, they might eventually crash into each other. But for an example, Pluto and its biggest moon are pretty similar in size. So if you were on Pluto, you would see a really big moon in the night sky. You'd see a really big moon because it's very big, just compared to the size of the planet you're on and how close they are. So yeah, you can have ridiculously big objects in the night sky. And I actually really like when sci-fi films do that, when you have like two moons or when you see rings of a distant planet. I think that's very cool. And as long as it's in a state where it's not too close to mess up the gravitate, like the orbit of the planets, I'm fine with that. So I'm not completely sure what your question was, but there is no limit to, other than gravity and messing up orbits, there's no real limit to how big or small objects should be in the night sky. Okay, just quickly glancing through the comments here. I think I've answered a lot of those. Then we did the Inflaton one. Then I see there's a question by Wayne and a few more questions to catch up with. Okay, let me just check a few more things here. ChatGPT once told me that many humans have an inherent bias to be suspicious about AI. Yeah, yeah. I think it's also there's a very interesting question there about how we treat things that we see as being inferior to us and then why we fear that they may rise up against us. Anyway, let's not go down that path. But yes, I'm not surprised that ChatGPT blamed the movies and stories because we often do have stories where there's a robot uprising, where there's an artificial intelligence uprising. And I think questioning that is very interesting. Like, why do we have all these stories? Where do they come from? But that's a whole other question that I am probably not equipped to dive into. Okay. A comment from David Howden here. I never feel comfortable with it just so happens, explaining the sun moon eclipse thing. Feels odd that this rather unusual thing happens on the only planet with no life. Yeah. Although, to be fair, like you can it might also be related, right? If you, as I was saying, if you're closer or further away from the sun, then your temperature would be different. The way the sun would appear in the sky would be bigger or smaller. But then if you're too close, if it's too big, you might not be able to have life. If it's too far away, you might not be able to have life. The moon helps regulate our tides. So it doesn't really like help there be life on Earth, but it is part of our system. Yeah, I feel like it's just in general it's considered a coincidence that these two are the same size. There's not really an intrinsic reason for it that we have found, but there might be some reason for it. Okay, back to questions. As always, if I forget a question, if I miss a question, I swear it's not intentional. There's just quite a few questions here, and sometimes I don't get through all of them. Okay. Let me just get to the question here. There was a question by Wayne. The universe is awash with electromagnetic radiation. When observing an object beyond a certain distance, how is it electromagnetic radiation isolated from everything else? Excellent, love that question. Now, the electromagnetic radiation, the universe has a very cool thing that things get redshifted. As I mentioned before, photons, particles of light have a wavelength. As they travel through the universe, this gets stretched. So it goes from being visible to being in a different range. So the universe is filled with electromagnetic radiation. The biggest one that we can think of is, again, the cosmic microwave background radiation. I'm spoiling you all today. This is like its 6th appearance today. So this is everywhere in the universe. If you look at anywhere in the night sky or in the day sky, this is behind everything else. This is electromagnetic radiation, particles of light that are everywhere in the universe. But we don't see them constantly with our eyes because these are in the microwave range of the electromagnetic spectrum, which we are not sensitive to. We cannot see microwave range. But if you had a species, like some random fish or a bird that could see in the microwave range, they would see the CMB constantly. But we haven't found species that do that because it kind of seems that the species that are on Earth have developed a vision that fits within the light produced by our sun, which is very, very cool. Then you also have things like distant galaxies producing light. Again, this is going to be redshifted. It's going to be outside of the visible spectrum. So the fact that we don't see constant light everywhere in the universe is because the universe is expanding and everything is redshifted, so that then not everything is in the visible spectrum. Then how is its electromagnetic radiation isolated from everything else? I guess that's if you're looking at a specific object, as you say here. then generally that object will produce a certain amount of electromagnetic radiation. For an example, a galaxy is not going to be in the microwave range of the electromagnetic spectrum. It's producing more energy. So then you can kind of subtract this known background, right? But then it gets more complicated. If you're looking at stars, you have to subtract the galaxy as well. So what you usually do is you figure out the big things that you can get rid of, and then you get rid of those to look at the things behind them. Or you change range. Something that is really cool with the JWST telescope is it's infrared instead of visual. So the Hubble Space Telescope was in the visual range of the electromagnetic spectrum, whereas JWST pushes it more to the ultraviolet, which means it can kind of to infrared. So it means it can kind of peer through the clouds and see different frequencies because it sees what's behind it. So the way we kind of isolate things is by removing the known backgrounds. Like, we know the CMB is there, but that's microwave, so let's ignore everything in the microwave range. Okay, we know a galaxy is there, and that's kind of emitting a lot of gamma rays. Let's move that out. And then you kind of separate the things that you know to try to figure out what the thing that's left is. And that's usually what we try to focus on. So hope that answers your question. As always, if not, please do let me know. Yeah, a mantis shrimp. Mantis shrimp can see like 27,000 colors. I have no idea why a mantis shrimp needs to see that many colors, but it can. So yeah, I'm not sure why a mantis shrimp needs to see so many colors, but they can. But I don't think a mantis shrimp can see the CMB. Okay, clarification from Scott here. You sent an email asking if the screensaver. Okay, yeah, you did send me an email, didn't you? Yeah. Honestly, there is now a folder in my Cup of Cosmology inbox called Not Answered. And there's about 6 emails in there that people who I promised an answer to and just moved your emails into that folder. So the chances of you getting an answer at this point are quite slim. But it might happen someday. Maybe. So yeah. But if you send me an email to contact@cupofcosmology.com, I do always say that if you ask me science questions on the email address contact@cupofcosmology.com, I might not always reply to them because I am very busy. My science outreach is something that is not part of my job. It's my hobby. I love doing it. I really love doing Cup of Cosmology. Please never feel bad about asking me questions. But if you send me a question via email, I usually try to answer it in a live stream because otherwise I'm going to spend so much time answering people's questions via email as well. So if you have sent me a question via Cup of Cosmology, if it's the short one that I can answer in 5 minutes, I have. If it's one that requires a longer answer, I've probably not got back to you. And I think that's the case with you, Scott. I remember your email was long and I was like, problem for later, and never got back to it. So yeah, if you ask me a question in Cup of Cosmology via the email address, you won't necessarily get a written answer, but I will try to answer you in the next stream if I remember. But do feel free to get in touch with contact@cupofcosmology.com, and I will always try to answer the questions. But as said, I can't always promise to answer all of them because otherwise it becomes too much. And now the question from Ian that I wanted to answer just now, but wanted to go to all the ones before that. So, question from Ian here. When did you begin your serious interest in astronomy, astrophysics? I'm sure you've been asked this many times, but curious. Yeah, so I think my interest in science started when I was really, really young. There's the fun story my family always tells that one of the first words that I learned to say was, "What's that?" So I was running around pointing at things, "What's that? What's that? What's that? What's that?" And at some point, my parents were like, "You have a science book, figure out the answers." So then I figured that science was the way to answer that question of what's that, and what's out there, and what's going on. And the more I got into physics, the more I realized that physics really could answer these questions. Then I think that always put me as a kid in the mindset of I want to do something. I want to figure out what's out there. I got my first set of binoculars, like really fancy binoculars to look at the stars when I was about 18. And it was a really nice pair of binoculars, and I love looking at the night sky. But at that point, I wasn't thinking about studying that. During my late high school years, so when I was probably around 16, 17, I had a very influential philosophy professor, and we were doing like history of philosophy. And I thought it was really cool about all of these philosophers trying to understand the universe trying to understand the world based on what knowledge they had. You know, when we were talking about Plato's solids and the ether and these things, we know that these are outdated ideas, but these were the first kind of cosmology opinions. These were, or not the first, no, sorry, because there were a lot of cosmology knowledge predating that. But it was kind of the first that I was exposed to of this idea of how to understand the world around us. And this philosophy teacher said to us one day, modern day philosophers are actually physicists. Physicists are the modern day philosophers, just backed up with a rigorous scientific method. I was like, that's kind of cool. So that's helped me get into physics. And then about the second year of my physics degree, so 1920, I think, yeah. I joined an astronomy group at my university. It was just like one guy and his telescope, and then we're like, let's make this an official association. So we set up the astronomy group, and I looked through the telescope, and I looked at the night sky and was like, what's that? What's up there? And at that point, I knew I wanted to figure out what was happening in the universe, like what was out there, what was going on. So then I took a course on Introduction to Astrophysics and Introduction to Cosmology. Now, Introduction to Cosmology was a course that was very interesting because I don't like how it was taught. I didn't get on that well with the teacher. It was a course that was done in a way that I wasn't likely to enjoy it. But I remember a specific lesson in cosmology. The first time we went through the mathematics of the CMB, the mathematics of this map here, this thing here. I remember this lesson. I remember sitting in that lecture room. I remember hearing about the mathematical description of the CMB and saying, that is what I want to work on. That is it. That is my thing. That was one of the year 3 of my undergrad. And at that point, it was like, okay, now I'm going to do a master's in cosmology. I'm going to do a PhD in cosmology because I want to work on that. So that's a long answer. Recap. How did I get into cosmology? How did I get into science? I think my parents equipped me with all the tools as a kid to actually ask these questions and try to figure out these answers, and got me really interested in kind of trying to figure out how things around me worked. Then I had a teacher who helped get me into physics, or helped convince me that physics was the right way to go. And then a combination of joining the astronomy group and taking my first cosmology course convinced me that cosmology was the way to go for me. And it's very funny because when I think back to that cosmology course, I don't have good memories of the way it was taught. I really don't have good memories of the lecturer in question. But I do have I have this like very vivid memory of how I felt when we went through the mathematics of the cosmic microwave background radiation. I remember being sat in the lecture room just like, oh, wow. That's an amazing feeling. And even though I don't work on the CMB anymore, just the fact that we can look at the universe and say like, hey, I understood what you did there. Yeah, we can look at the night sky and try to figure out 14 billion years of cosmic evolution. We can take these random spots of light in the night sky and say like, haha, look, I found out how galaxies work. The fact that we can do this is incredible. The fact that I can be part of this journey still amazes me. And it's just so cool. You know, I'm working on some random invisible matter in the universe that we have no idea what it does. We can't see it. And yet physicists are here like, I think I know how to do this. I'm going to figure this out. Something that I'm working on these days, which I talked about extensively last week, is gravitational waves. Tiny, 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 insignificant ripples in the fabric of the universe. And we're just like, you know how we're going to measure these? With lasers. And we've built amazing machines with lasers to measure these tiny ripples in space-time. And if that's not cool enough, now we're sending a mission to space. So like we're going to send a satellite to space that's going to shoot lasers back and forth between 3 little baby satellites to try to measure ripples in the universe produced 14 billion years ago. How cool is that? How could I not want to work on this? Yes, it is mind-blowing that we are having these conversations, that we can ask these questions, that we can figure out how to answer these. Yeah, so I definitely think influential parents, influential teacher, this had a big impact on me. The fact that there were people in my life who encouraged me to do it had a big impact on me, and also a heavy amount of spite, because I feel like spite is a good motivator. And the amount of people, especially guys, who have told me that I don't belong in academia, that I don't belong in physics, that I'm not what a traditional scientist looks like. You will never make it in science because. Just to prove those people wrong, that is a very good reason to continue in physics. That's that's not such a pretty story, but it is true that when someone is like, you can't do it, I'm like, watch me. And anyway, here I am, many years later into academia, and yeah, running still on the fact that I just completely lost studying the universe and a heavy dose of spite. Because, you know, it's fun. I see a few comments here about this. So a comment here from me, and it was a philosophy professor in high school too. That is amazing. I really like that. You know, you and I work on very different topics. So Ian, again, no scientist, but it's very cool that a philosophy professor could convince us that this is the way to go. But yeah, and a comment here also by Ian, it's honestly so terrible that more students don't have the privilege of having these gifted instructors. I agree. I really do agree. Like, I think having a good teacher can be life changing. You know, I remember all of the good teachers I've had. I also remember all of the very terrible teachers I've had, and the ones that have impacted me for better or worse. I remember the people who I thought, if I'm ever a teacher, I'm never going to be like you. And I remember the teachers where I've learned stuff from and thought, like, you are modeling the type of learning that I want to see. And it's actually something that I'm very invested in now. Is I remember in my university days, in my undergrad days, I remember being extremely frustrated by a lot of teachers, by a lot of lecturers, by having the impression that a lot of people were just there to dump their knowledge and they didn't care if the students learned or not. So something that I'm really putting a lot of effort into now is trying to be the type of lecturer at university level that I would have liked to see. So I have taken courses on like how to be a good university professor. It's something that I care about a lot because I feel like if you can reach people in a good way, it's just so much better. Like the best courses I've had are usually because of a good teacher. So I think that's important, and especially something that's important at younger ages, like primary school, high school. That is where you can really develop a kid's interest in topics. Those ages are crucial. And if at those ages you have someone who's just like, I'm not going to bother teaching you, it's just terrible. So I very much agree with what Ian just said here, that having a good teacher is a privilege. And I really think we should do more to reach people of every age and tell everyone about how amazing being a scientist is, and not just a scientist, like every topic. But yeah, I think you can't underestimate the importance of a good teacher. And as I said many times, Scott, it is never too late to pursue what you're interested in. You know, I genuinely believe that at any point you can just follow what you want to do. Of course, there's always going to be limitations, unfortunately. But I think it is never too late to just decide, you know what, career change, time to do something new, time to do something different. Currently, I'm in a Swedish course where I'm trying to learn Swedish. It's going somewhat well. And there's someone in this course who's in his 80s and he's learning Swedish to keep his mind fresh. And I love that because I'm there learning Swedish so that it increases my chances of staying in Finland because Swedish is an official language here. And he's just there like, I'm 80. I've decided to learn Swedish. And you know, good for him. I love this. I think you are never too late to do what you want to do in life. And I feel like we got very philosophical here at the end, but I do like the question of why I went into science because it's always a nice reminder of why I'm here and why I'm doing this. And also why I love chatting to everybody about science, because I remember how important it was for me to have people in my life talk about things and tell me about these things. And, you know, if anybody watching here, if I can convince you that physics is great, that you should care about these things, and this is my purpose here. This is also why I go and give talks at high schools or at observatories, because it's about telling people about all of the cool things. And I think that's a very fun thing to do as well. And then there was this question by Ange about mantis shrimp, of how do we know they see that many colors? And that is a great question because, of course, you can't really ask them like, hey, shrimp, how many colors do you see? And then there's a whole fun discussion we can have about what it even means to see color. Like if I see red, is it the same as what it means when you see red? Are our brains processing this information in the same way? That is a whole other question that we can get into. So how do we know how many colors shrimp can see? Well, we have a pretty good understanding of how eye receptors work. And it turns out if you dissect animals, you can dissect their eyes as well. And you can see based on like just pulling apart their eyes, how many light cones they have and the range of frequencies they're sensitive to. And it's impressive. So yeah, it's basically, unfortunately, the way we know a lot of things about animals is what happens when you dissect it to learn about it. And that's what we've done to a lot of animals. Also, one of my favorite animal facts that I relearned recently is that snails have teeth. And in fact, snails have like 20,000 teeth. They're actually the animal that has the most teeth. They're like, why do snails need teeth? Why is this knowledge we should have? The way we know this is, again, by kind of like poking at a snail and figuring this out. Why do snails have 20,000 teeth? No idea. Why do they need that many? I do not want to know, but hey, fun fact. I bet you did not come to Cup of Cosmology today expecting to learn this random fact about snails, but here we are. So, yes. A comment from David Howden here. I've seen photos taken with fiber optics poked into a dissected moth eye. Yeah. Then you figure out how do moths see, how do other animals see, is by kind of putting a camera inside their eye and seeing what happens. Unfortunately, that is how we learn a lot of things about animals. Anyway, I am deeply perturbed, deeply disturbed by the fact that snails have 20,000 teeth, and I just wanted to share that random fact with you all. Yes, not cosmology related in any way. Probably not what you signed up for today, but here we are. Okay. I'm not sure if I want to end this conversation on snail teeth, but I have gone through all of the questions and we are at the 1 hour mark. I love the variety of questions we've had today. Like we've gone from, of course, I started with CMB, we've gone through dark energy and X-rays and machine learning and some fun tangents on the way, some really fun topics, standard model particles, gravitational waves. It's been really, really fun. And I love the question, Ian, about why I got into science. It is a very cool question. And it is one that I get asked often, but it is one that I'm always happy to answer because it is very cool to talk about. And it does remind me of just why I'm here and why I'm doing this. And yeah. So thank you everyone for the questions. It really has been great fun. I hope you all learned something today. If the one thing you took away from this conversation is snails, that's also fine. Sometimes we go on random discussions and that's okay. So next week should be 25th. Next week should be Sunday 25th. I'm just checking my calendar because honestly, I have so many things happening these days. It is hard to keep track. But I do not appear to have anything in my calendar next week, which means Cup of Cosmology should be back online next Sunday, same time as always. That is 8 p.m. if you're in Finland, 7 p.m. if you're in the rest of mainland Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone. Please do feel free to check that out. As always, if you have any unanswered questions, feel free to email me, contact@cupofcosmology.com. As I said during the stream, I don't necessarily always answer questions via email, but I will do my best to get back to you all, or at least acknowledge that I've received your email and seen it. And, I will try to give you some type of answer. As always, feel free to get in touch. So thank you everyone for joining. This has been super fun, lots of fun questions, lots of random questions. It was great to see Ian in the chat again. I'm not sure if Ian is still active on any streaming service, but please do follow him on whatever social media you're on. It has been great to see everybody here again. I hope to see you all again next Sunday, same time as always. And I hope in the meantime, you all stay safe and take care of each other.